Hi all, welcome to the lecture series on Aerospace Propulsion. Myself, Manideep Gupta, Assistant Professor from Department of Aeronautical Engineering, MLR Institute of Technology. Today, the topic which we are going to discuss is about the action time, burn time, and also the ignition problems that occur during the combustion of solid propellant rocket motor. So, coming to the overview of today's presentation, we'll discuss the action time, burn time, how do we calculate the action time and burn time, and all the problems that happens during the ignition of solid propellant rocket motor and their solutions. So, coming to the first one, action time and burn time. Here you can see the diagram. Okay, this diagram consisting of pressure on the y-axis and time on the x-axis, right? And this diagram is given with some numbering. It has a variation of pressure with respect to time when the solid propellant rocket motor burns. Okay, here this is a point C and this is a point A, and here you can see a point B and D here. Okay, so the pressure is rising like this. Okay, and we have drawn two tangents here, one tangent here and one tangent at here. So, whatever the intersection point, that intersection point we are considering as A, and after some duration the pressure suddenly decreases. It starts decreasing at the end of the propellant grain burning. So, at that time again we are drawing one tangent here and another tangent here. Okay, and whatever the intersection point we are noting that that as PWF, Webb final pressure. Okay, Webb initial pressure. Okay, and this point is B. Okay, and here this is the point C. C is a point where the pressure is 10% of the initial Webb pressure. Okay, and D is the point where the 10% of the pressure, final Webb pressure. Okay, so we'll see the action time and burn time here now. So what is action time? So the action time is nothing but the time taken between the pressures of 10% of the initial Webb pressure. Where is initial 10% of initial pressure? This is C. Okay, and 10% of the final Webb burn pressure. So this is the 10% of the final Webb burn pressure, that is D. Okay, so that is nothing but the time taken from C to D. The time taken from C to D is nothing but action time. It is denoted with the TA, action time, right? So we cannot consider the pressure from 0 to 0. We are not considering from 0 to 0. We are considering the 10% of the initial Webb pressure to the 10% of the final Webb pressure. So that is nothing but we are considering as a action time. Action time. The next one is burn time. Burn time means the duration in which we will get the maximum energy from the burning process. Okay, the burn time is defined as the time required from the burning of the web of the solid propellant grain. Okay, the main propellant grain burns, whatever the duration in which the total propellant grain burns. Okay, that is a burn time. Okay, the time corresponding to the intersection of the tangent to the ignition portion of the tangent to the web burning portion in the pressure time plot is corresponding to the starting of web burning. Okay, this is the starting of web burning, which is the intersection of the two lines. Okay, which is the intersection of the two lines drawn to the pressure time plot, and the intersection of point B between the tangent of the web burn phase and tangent of the tail off phase. So tail off phase means wherever the point after which the pressure starts decreasing. This is a tail off phase. Okay, this is the tangent drawn at the tail off phase. Okay, and this is the tangent drawn at a web burn phase. The intersection point is nothing but the B, and whatever the duration between A and B, this is nothing but burn time. This is nothing but burn time. Okay, so this is nothing but called as completion of the burning of the web. Here in this region we will get a maximum amount of the thrust. Okay, during this region the thrust produced by the rocket is less. It is even though we'll get some amount of thrust, but it is not actually useful. Okay, so that's why the burning time is very important. Burning time is important, and even this difference between burn time and action time is also very important. Okay, the time taken to reach the web pressure, initial web pressure, is also matters for instantaneous burning of the propellant grain. Okay, so this is about action time and burn time. Next, we will discuss the general ignition problems. Okay, ignition problems and solution. So generally, what happens? Why ignition? Why problems comes in the ignition process? Okay, we have gone through the loading strategies of propellant grains, right? So there are two types of loading strategies. One is cartridge based, and one other is freestanding, right? What happens is we make the propellant grain by casting process. Okay, we'll place the total powder of the propellant grain, we'll mix with the binders, and we'll make the solid like a powder into a solid form of the propellant grain. What happens is during this process there will be some stresses developed in the propellant grain. Okay, so whenever the propellant grain starts burn, it will release it will undergo high pressure in the high pressures and temperatures because of the burning. Okay, so whatever the propellant grain structure, that should resist these pressures and temperature. If the propellant grain structure is not properly made, okay, because of this high pressure and temperature, the grain structure may collapse and the total rocket will get a fire. Okay, this will lead to a drastic failure of the rocket motor. Okay, so what we do is we go for a stress analysis. We go for stress analysis in rocket motors to design the configuration of the grain that stresses and strains may lead to the failure. Whatever the stresses and strains developed in the propellant grain should not lead to the failure. That's why we will go for some stress analysis. We will go for stress analysis of the propellant grain. Why? And the static and dynamic loads and stresses are also imposed in the propellant grain. So this is also one reason for propellant grain failure. So we have to overcome this. So during the this static and dynamic loads transferred to the propellant grain during the manufacturing, during the transportation, storage and operation. So we should reduce these stresses, whatever the stresses during the manufacturing, transportation, storage and operation. So this is one of the very important ignition problem that happens. Most of the times the solid propellant grains, solid propellant rocket motors fails by the ignition phase itself, because of the grain does not sustain the stresses developed due to the high pressure. Okay, structurally a rocket motor is a thin shell almost completely filled with a viscoelastic material, and the propellant, which is normally accounts for 80 to 94% of the motor mass. Okay, 80 to 94% of the motor mass is occupied by only the propellant itself. So propellant have some mechanical properties. Okay, each propellant will have different mechanical properties that are not found in ordinary structural materials. Okay, and to date this have received relative little study. Even we should go for because of this different mechanical different properties of the propellants, we should go for a more research to avoid the failure at the time of ignition process. So whatever the viscoelastic nature of the solid propellants is time history dependent, and these materials accumulate damage from repeated stresses. This is known as cumulative damage phenomena. Whatever the even though the load applied on the propellant grain is very small, but because of this continuous applying load during the different stages like manufacturing, transportation, storage and operation, these all stresses will completely combine and will give a cumulative damage effect, when at the time of propellant burning. So most common failures that occurs. Okay, the most common failures occurs due to the surface cracks in the solid propellant grains. What happens? So what is surface cracks? Surface cracks that are formed when the surface strains are excessive. Generally cracks happens on the surface when the strains develop in the propellant grain is excessive, they open up additional burning surface. If the surface is like this, okay, the water, this will okay. But whenever the crack forms, what happens? It will open the additional burning surface. This burning surface also increases. So the burning surface will increase because of the crack formation. So when the burning surface increases, the pressure fluctuations happens in the motor. Okay, so this will cause chamber pressure, a change in chamber pressure as well as a thrust to increase suddenly. Okay, so the higher or shorter duration thrust may cause the vehicle to fly a different trajectory, and this may result in the missed mission objective. So what happens? Generally, we plan the thrust profile during the mission, right? So because of these cracks, whenever suddenly the ignition, the thrust increases, what happens is the vehicle trajectory will change. Whenever the vehicle trajectory changes, sometimes even we lose the vehicle away from the trajectory, and mission also fails sometimes. Okay, so mission objective will get effect because of this cracks formation. So with these cracks, suppose small, if the cracks increase with many cracks or a few deep cracks, the case becomes overpressurized and also fails. If the more cracks are formed, and the deep cracks, if the cracks are deeper, then there is a huge change in the chamber pressure. If the chamber pressure exceeds the limit of a motor case, then there is a chance of failure of motor case completely. So it is a very, very serious parameter to be observed for proper burning of the solid rocket motor. Surface cracks play a very important role in the ignition process of a solid rocket motor. So at a higher strain rates, deeper, more highly branched cracks also forms. When the strains increases, when the propellant strains are already there, and cracks also increase. The number of cracks increases when the pressure in the chamber increases during the second phase and third phase of the ignition process. So this is the one of the main common failure type of a solid propellant rocket motor. Next is a small locally detached or broken unbounded area. Locally detached or broken unbounded area. So what happens? This happens whenever happens because of the mistakes done while manufacturing the propellant grain, while mixing the binder with the propellant with the powder material. If the powder material and binder is not mixed proportionately, then these type of failures occurs. Locally detached surfaces and broken unbounded areas happens. So what happens is, small locally detached or broken unbounded area may also exist in the grain periphery. Okay, a very thin gap may form between the propellant and liner or the case or the insulation. So because of this unbounded area, whatever the gap, some gap will be maintained. Okay, some gap comes between the liner and the propellant grain or the motor case. So it can be seen with the help of X-rays or proper heat conduction instruments. Right, this should be avoided. Okay, if the propellant grain is not bonded to the motor case properly, it will detach from the motor case. Okay, as any part of such unbonded areas become exposed to the hot or high pressure combustion gases in the grain cavity, the designed burning area increases suddenly. When the designed burning area increases, the pressure in the chamber also increases suddenly. Okay, such enlarged burning area results in higher chamber pressure and larger thrust. So having even a few large unburned areas often results in rocket motor failures. This sudden pressure increase because of unbounded area also leads to the rocket motor failure. One is surface cracks, one is unbounded or locally detached propellant grains. So these are the two main ignition problems we can observe while burning the propellant grain. Next, there are other types of other failure modes also there, like having a high enough ambient grain temperature to cause a large reduction in the physical strength of the properties. So the propellant grain is a substance, right? Any substance will possess different properties at different temperatures. So when the propellant grain exposed to high temperature, the properties will change. The grain properties will change, and the physical strength may get effect. This is also one type of failure. The chance of one type of failure happens in the propellant grains. And next, air bubbles, porosity, and even uneven density. The mixture is not the binder and powder is not mixed up thoroughly. Then density also, uneven density distribution also happens. So like a grain may locally reduce the propellant strength to cause failure and cracks by deep bonds. This also happens. Okay, so manufacturing is a very important phase. Manufacturing the propellant grain is very important phase for good combustion of the propellant grain. So this will be avoided. We can go for inspection. Before loading the propellant grain in the motor case by doing some inspections. We can go with the X-ray inspections are routinely used by manufacturers, which can detect all but the smallest debonded areas and surface loss. So we can the X-ray if the debonded area is large, we can detect with the X-ray. But if the bonded area is small, it can detect that small bonded areas. But sometimes if the small debonded areas are more, then that will also lead to the motor failure. Okay, when the X-ray inspection uncovers debonding or cracks that cannot be tolerated, so the solid propellant unit is rejected and scrapped. If the if the inspection if it founds more debonded areas, if the density distribution is not proper, we should not use that propellant grains. We can send to scrap. So other failure modes are excessive deformation of the grain. One more thing is a deformation of the grain. The grain shape may deform, the grain thickness may deform because of the high temperatures and stresses undergone by the propellant grain. So this is also one of the reason for rocket motor failure. Grain deformation. Next, so these are the summary of today's topic. Right? We have gone through the action time, burn time, and we have gone through the ignition problems and solutions like surface cracks, small local debonded areas, and the propellant grain deformation. All these are the reasons for motor case, and we can avoid this with the help of inspections before loading the propellant grain into the motor case. So this is about the today's topic, and we'll discuss. We'll continue to the next topic in the next lecture. Thank you.